Welcome to today's problem discussion. In this session, we'll tackle LeetCode problem number 1491, average salary excluding the minimum and maximum salary. This is a great problem to strengthen your understanding of array manipulation and mathematical logic. Let's dive in and explore the solution together. In this problem, we are tasked with calculating the average salary of employees, but with one key condition: we need to exclude the minimum and maximum salaries from the calculation. The input is a list of unique integers, where each integer represents an employee's salary. The result should be a floating point number that represents the average, rounded to 5 decimal places. For example, if the input list is 4,000, 3,000, 1,000, 2,000, we will exclude the lowest salary, which is 1,000, and the highest salary, which is 4,000, leaving us with the values 3,000, 2,000, to calculate the average. The output is expected in a standard floating point format with 5 decimal places for precision. For the first example, the input list is 4,000, 3,000, 1,000, 2,000. The minimum salary is 1,000, and the maximum salary is 4,000. After removing these two values, we are left with 3,000, 2,000. To find the average, we add these remaining values, resulting in 3,000 plus 2,000 equals 5,000, and divide by the number of elements, which is 2. The result is 5,000/2 equals 2,500.0. Since the problem requires the result to be rounded to 5 decimal places, we return 2,500.00000. This shows how the calculation works step by step. In the second example, the input list is 1,000, 2,000, 3,000. Here, the minimum salary is 1,000, and the maximum salary is 3,000. After excluding these values, we are left with a single element, 2,000. The average of a single number is the number itself, so the result is 2,000.0. Again, the output is formatted to 5 decimal places, so the final result is 2,000.00000. This demonstrates how the calculation handles cases with the smallest possible valid input size of 3 elements. Now, for the third example, the input list is 6,000, 5,000, 4,000, 3,000, 2,000, 1,000. The minimum salary is 1,000, and the maximum salary is 6,000. Once we remove these values, the remaining salaries are 5,000, 4,000, 3,000, 2,000. To calculate the average, we add these values together: 5,000 plus 4,000 plus 3,000 plus 2,000 equals 14,000. Then, we divide by the number of elements, which is 4. This gives us 14,000/4 equals 3,500.0. After rounding to 5 decimal places, the result is 3,500.00000. This example highlights how the solution works with larger lists. Finally, let's consider a scenario with evenly spaced salaries. For example, if the input is 1,000, 2,000, 3,000, 4,000, 5,000, the minimum salary here is 1,000, and the maximum salary is 5,000. After removing these values, the remaining salaries are 2,000, 3,000, 4,000. Adding these together gives 2,000 plus 3,000 plus 4,000 equals 9,000, and dividing by the number of elements, which is 3, results in 9,000/3 equals 3,000.0. The result is returned as 3,000.00000. This illustrates that when salaries are uniformly distributed, the average of the middle values is simply the midpoint of the range. To solve the problem of calculating the average salary excluding the minimum and maximum values, we considered multiple approaches, beginning with a brute force method. The intuition behind this approach is straightforward. First, we identify the smallest and largest salaries in the array using Python's built-in min and max functions. Then, we iterate through the array, summing all the values except for these two extremes. Finally, we calculate the average by dividing the adjusted sum by the count of the remaining salaries. While this approach is simple and leverages basic operations, it involves multiple scans of the array, which we'll analyze further in terms of efficiency. Analyzing the complexity of the brute force approach, its time complexity is O(n), because we perform 3 separate traversals of the array, one to find the minimum, another for the maximum, and a final loop to compute the sum of the remaining elements. The space complexity is O(1), as we don't use any additional data structures. However, this solution has some drawbacks. Specifically, the repeated passes over the array introduce redundancy, which could be avoided. To address this inefficiency, we considered an optimized single-pass approach. This method combines the steps for finding the minimum, maximum, and sum into a single traversal. By doing so, we eliminate the need for multiple loops and improve the algorithm's performance. The steps involve initializing variables for the minimum, maximum, and total sum, then updating them dynamically during one pass through the array. After traversing the array, we subtract the minimum and maximum from the total sum and divide the result by the number of remaining elements. The optimized single-pass approach offers significant advantages over the brute force method. By reducing the number of iterations from 3 to 1, it minimizes computational overhead and makes the algorithm cleaner and more efficient. Additionally, we explored an alternative approach involving sorting. The intuition here is to sort the salary array, exclude the first and last elements, and compute the average of the remaining values. However, this method has a higher time complexity of n log n due to the sorting step. While sorting simplifies the process of finding the minimum and maximum, it introduces unnecessary overhead because the problem only requires these two values, not the sorted order of the array. Furthermore, sorting may require additional space if it's not done in place. For these reasons, the sorting approach is less efficient compared to both the brute force and single-pass methods. After evaluating the different methods, the optimized single-pass approach emerged as the best solution. With a time complexity of n and a space complexity of 1, it is both time-efficient and space-efficient. The key insight lies in the realization that the minimum, maximum, and total sum can all be calculated in a single traversal of the array, avoiding redundant operations. This makes the algorithm not only optimal but also clean and easy to implement. The brute force approach, while simpler to conceptualize, was rejected due to its multiple passes over the array, which are less efficient. Similarly, the sorting approach was discarded due to its higher time complexity and unnecessary overhead. By choosing the single-pass method, we achieve an elegant balance of simplicity, efficiency, and clarity, making it the ideal choice for solving this problem. To begin, the problem involves calculating the average salary of employees, but with a twist, we need to exclude the minimum and maximum salaries from the calculation. The input is an array of integers where each element represents an employee's salary. It's guaranteed that there are at least 3 salaries in the list, so we don't need to worry about edge cases like insufficient data. The algorithm starts with input validation, though explicit checks aren't strictly necessary given the guarantee. Next, we initialize 3 variables, min_salary to a very large value to track the smallest salary, max_salary to a very small value to track the largest salary, and total_salary to 0, which will accumulate the sum of all the salaries. These initializations set the stage for efficient processing as we move through the array. Now, we proceed to iterate over the array of salaries. For each salary, we compare it to our current min_salary and max_salary and update these variables as necessary. At the same time, we add the salary to the total_salary. By the end of this loop, we will have determined the minimum and maximum salaries as well as the total sum of all salaries. Once the loop completes, we exclude the minimum and maximum salaries by subtracting their values from total_salary. This adjusted total represents the sum of the remaining salaries. Finally, to calculate the average, we divide this adjusted sum by n2, where n is the total number of salaries. The subtraction accounts for excluding the 2 extreme values. The result is then returned as a floating point number, completing the algorithm. The algorithm's design has some key insights that make it both efficient and elegant. First, it uses a single pass through the array to compute the total sum, minimum, and maximum values, which ensures a time complexity of n. This is much faster than alternative approaches like sorting, which would increase the complexity to n log n. By avoiding sorting, we maintain efficiency. Additionally, the guaranteed input of at least 3 salaries simplifies the implementation, as we don't need to handle scenarios like empty arrays or arrays with fewer than 3 elements. The algorithm's reliance on simple primitive variables, min_salary, max_salary, and total_salary means it is also space efficient, with a space complexity of 1. This combination of linear time complexity and constant space usage makes the solution highly optimized. Let's analyze the complexity and walk through an example. The time complexity is O(n), as we only loop through the array once. The space complexity is O(1), because no additional data structures are used, all intermediate results are stored in a few variables. For the example, consider the input salary equals 4,000, 3,000, 1,000, 2,000. We start by initializing min_salary as infinity, max_salary as negative infinity, and total_salary as 0. These initial values help us correctly update the variables as we process each salary step by step. Now let's perform the iteration. The first salary, 4,000, becomes both the min_salary and max_salary, and it is added to total_salary, making the total 4,000. Next, 3,000 is processed, updating min_salary to 3,000 while keeping max_salary unchanged at 4,000, and the total becomes 7,000. Then, 1,000 updates min_salary to 1,000, leaves max_salary at 4,000, and brings the total to 8,000. Finally, 2,000 keeps the min_salary and max_salary unchanged, and the total becomes 10,000. After the loop, we exclude the minimum and maximum values by subtracting 1,000 and 4,000 from the total, leaving us with 5,000. Dividing this by 4 to 2 gives 2,500 as the average. The output is 2,500. Lastly, we consider edge cases. If all salaries are the same, such as salary equals 1,000, 1,000, 1,000, the algorithm would exclude the minimum and maximum, resulting in a sum of 0 and hence an average of 0. For large inputs, the algorithm remains efficient due to its linear time complexity, so it can handle large datasets without performance issues. This robustness, combined with its simplicity, makes the algorithm well-suited for a wide range of scenarios. This implementation solves LeetCode problem number 1491, average salary excluding the minimum and maximum salary. The goal is to calculate the average of an array of salaries after excluding the minimum and maximum values. Here's a step-by-step explanation of the code. 1. We define a method average inside the solution class. This method takes a list of integers salary as its input, where each integer represents an employee's salary. 2. To exclude the minimum and maximum salaries, we first use Python's built-in min and max functions to find the smallest and largest values in the input list. These two values are stored in min_salary and max_salary respectively. 3. Next, we calculate the total sum of all salaries in the list using Python's sum function. To exclude the minimum and maximum salaries, we subtract min_salary and max_salary from the total sum. This ensures that only the remaining salaries contribute to the sum. To compute the average, we also need to know how many salaries remain after excluding the minimum and maximum. Since the input guarantees at least 3 salaries, the count of remaining salaries is simply len salary 2, the total number of salaries minus the 2 excluded values. 5. Finally, we calculate the average by dividing the adjusted sum, total_sum, by the count of remaining salaries, count. The result is returned as the output of the method. This implementation is efficient, with a time complexity of O(n), where n is the length of the salary list. This efficiency is achieved because the min, max, and sum operations each require a single pass through the list. The space complexity is O(1), as no additional data structures are used, and all operations are performed in place. The code handles all edge cases, including scenarios where the list contains exactly 3 salaries, the minimum allowed. It leverages Python's built-in functions for simplicity and readability, ensuring clarity and maintainability. This is the Java implementation for LeetCode problem number 1491, average salary excluding the minimum and maximum salary. The code mirrors the Python logic provided, with adjustments for Java-specific syntax and data types. Key differences include the use of int and double-for type declarations, math.min and math.max for finding the minimum and maximum, and explicit casting to double-for division. The core logic remains the same: iterate through the array to calculate the total sum and find the minimum and maximum, then compute the average by excluding these extreme values. To solve this problem, we start with the first example where the input is a list of salaries, 4,000, 3,000, 1,000, 2,000. The first step is to find the minimum and maximum salaries in this list. The smallest salary is 1,000, and the largest is 4,000. Once we've identified these, the next step is to calculate the total sum of the salaries while excluding the minimum and maximum values. The total sum of all salaries is 4,000 plus 3,000 plus 1,000 plus 2,000, which equals 10,000. From this, we subtract the minimum and maximum, 1,000 and 4,000 respectively, leaving us with 5,000. Now, we determine how many salaries remain after excluding the minimum and maximum. Since the input list has 4 elements, and we exclude 2, we are left with 2 salaries. Finally, to find the average, we divide the total sum of the remaining salaries, 5,000, by the count, 2. This gives an average of 2,500.0. The result of the first example is an output of 2,500.0. Now, let's consider a different scenario where all elements in the salary list are the same. For this example, the input is 2,000, 2,000, 2,000. In step 1, we find the minimum and maximum salaries, which are both 2,000 since all the values are identical. For step 2, we calculate the total sum excluding the minimum and maximum. Adding up all the salaries gives 6,000, and subtracting the minimum and maximum, which are both 2,000, leaves us with a total sum of 2,000. Then, for step 3, we calculate the count of salaries after exclusion. With 3 elements in the input list and 2 excluded, the count is 1. Now, in the final step for this example, we calculate the average by dividing the total sum, 2,000, by the count, which is 1. This results in an average of 2,000.0. So, the output for this example is 2,000.0. Let's explore one more case where the input includes a large range of salaries. The input list here is 1,000, 2,000, 3,000, 4,000, 5,000. First, we identify the minimum and maximum salaries. The smallest salary is 1,000, and the largest is 5,000. Next, we calculate the total sum of all salaries while excluding these values. Summing all the salaries gives 15,000, and subtracting 1,000 and 5,000 leaves us with 9,000. Next, we determine the count of salaries after excluding the minimum and maximum. Since the input has 5 elements and we exclude 2, the remaining count is 3. Finally, we calculate the average by dividing the total sum, 9,000, by the count, 3. This results in an average of 3,000.0. Therefore, the output for this example is 3,000.0. With this approach, we've demonstrated how to calculate the average salary excluding the minimum and maximum for various scenarios. To analyze the time complexity, let's break the solution into its main steps. First, we use the min function to find the smallest salary in the list. This function needs to iterate through the entire list once, making its time complexity O, n, where n is the number of elements in the list. Similarly, the max function also iterates through the list to find the largest salary, which is another O, n, operation. Next, the sum function computes the total sum of all salaries by iterating through the list once more, which again takes O, n, time. After these operations, we perform 2 subtraction operations to exclude the minimum and maximum salaries. Since subtraction is a constant time operation, its complexity is O(1). Lastly, we calculate the count of salaries excluding the extremes using the len function and a simple subtraction, both of which are O(1). Together, these steps give us a clear breakdown of the time complexity for each operation in the solution. Now, focusing on the computation of the average, we perform a division operation, which is also O(1). When we combine all the steps, the total time complexity is the sum of O(n) for min, O(n) for max, O(n) for sum, and O(1) for the remaining operations. This simplifies to an overall time complexity of O(n), as the linear operations dominate. Shifting attention to space complexity, the solution does not require any additional data structures. It only uses a few scalar variables like min_salary, max_salary, total_sum, and count, all of which occupy constant space. The input list salary is already provided as part of the function call, so no extra memory is allocated for it. Therefore, the space complexity is consistently O(1), regardless of the size of the input. When comparing this optimized solution to a brute force approach, the differences become clear. A naive method might involve sorting the salary list, removing the smallest and largest elements, and then calculating the average. However, sorting the list has a time complexity of O(n) log n, which is less efficient than the current solution's O(n). The space complexity for sorting could be O(1) if done in place, but it might increase to O(n) depending on the implementation. The provided solution is more efficient because it avoids the overhead of sorting and performs all necessary calculations in linear time. By leveraging built-in functions like min, max, and sum, it reduces the number of iterations in memory usage. Lastly, the time complexity remains O(n) in all scenarios, whether best, average, or worst case, as these functions always require a full traversal of the list. Similarly, the space complexity is consistently O(1) across all cases, making this solution both time and space optimal. When solving this problem, there are several common mistakes to watch out for. First, it's easy to overlook edge cases, such as when the array contains exactly 3 elements. In this scenario, excluding the minimum and maximum leaves only one value, which must be handled correctly. Another mistake is using sorting unnecessarily. While sorting makes it straightforward to identify the minimum and maximum, it introduces an O(n) log n time complexity, which is inefficient compared to linear solutions. Additionally, hard-coding indices, like assuming the first or last element after sorting corresponds to the minimum or maximum, can cause issues if the array isn't sorted as expected. It's always safer to calculate these values dynamically. You should also ensure that division by 0 doesn't occur, even though the constraints guarantee an array length of at least 3. Lastly, be mindful of precision loss, especially in languages like Python or Java, where integer division might yield incorrect results. Always ensure the final result is a floating point value when required. To tackle this problem efficiently, the optimal approach is to process the array in a single pass. During this traversal, you can simultaneously compute the sum, minimum, and maximum values, achieving an O(n) time complexity with O(1) space. This demonstrates a key pattern, filtering data while performing aggregations. Recognizing such patterns is valuable for solving similar problems. In an interview, you might start with a less efficient approach, like sorting, but it's important to articulate why it's suboptimal and how you can improve it. This showcases your ability to optimize. Also, pay close attention to the problem's constraints. For instance, knowing that the input will always have at least 3 elements allows you to make certain assumptions, but you should still validate your solution for edge cases within those bounds. This problem shares similarities with other LeetCode challenges. For example, LeetCode 414, third maximum number, also involves identifying extremes in an array. Similarly, LeetCode 1827, minimum operations to make the array increasing, requires iterative updates to an array while adhering to specific rules. Another related problem is LeetCode 121, best time to buy and sell stock, which focuses on efficiently tracking minimum and maximum values. Lastly, LeetCode 1281, subtract the product and sum of digits of an integer, is a simpler problem that can help you practice basic aggregation logic. Now, in terms of approaches, sorting is a straightforward but less efficient method, with O(n) log n complexity. A 2-pass linear approach, where you first find the min and max and then compute the sum, is simpler but not as optimal as a 1-pass solution. The most efficient method is a 1-pass linear approach, where you calculate the sum, minimum, and maximum in a single traversal, minimizing both time and space complexity. To summarize, always aim to avoid unnecessary operations, such as sorting, when a more efficient linear solution is available. Carefully validate edge cases, like arrays of the minimum length, to ensure your solution is robust. In interviews, focus on explaining your thought process clearly, discussing the trade-offs of different approaches, and demonstrating your ability to optimize for efficiency. Ultimately, mastering these techniques will not only help you solve this specific problem but also prepare you for tackling similar challenges in the future. Great job! To summarize, we covered the key points of solving problem number 1491, focusing on efficient array handling and mathematical operations. Remember to practice similar problems to strengthen your skills. Thank you for watching, and don't forget to like and subscribe for more content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!